Hello, everyone. Thank you for joining my talk. Today, I'll be presenting on change analysis across version history of Simulink models. First, what is Simulink? Simulink is part of the MATLAB toolbox. It's a software that we use to design, model, and simulate dynamic systems. So it has a graphical interface, and it also provides support for extensible third-party libraries to aid in your user a customized way for you to model or simulate dynamic systems. And currently, it has over 4 million users. So that's a large number of users. So we want to discuss how to the analysis of the changes that have been made to these models. So software evolution is about change and alternate choices. For example, this is a model that was created on January 20. So due to external factors, we had to add a new feature to the model, which is shown by the model element C here. But after some time, we found out that the relationship between B and C is a bit problematic, and it's actually preferable that we maintain a two-way pathway between A and C, such that it is actually preferred that for you is much more preferable to get to B by going from C to A than B, rather than having a direct relationship between B and C. So these are some of the choices that informs the reason why we make changes to software. But the reason why the changes were made are usually lost after a long period of time, and this lead to some use of a lot of maintenance issues like repetition of past mistakes, increased maintenance costs, and so on. So my goal in this talk is to prefer ways to analyze these changes in order to help us mitigate these challenges. So I do this by going through the evolution history in Simulink repositories. I extract those evolution history, get the changes between them, then analyze those changes to understand why the changes were made and the immediate impact of those changes. So my talk will focus both mostly on 2 points: why the changes were made in form of design decisions, and the immediate impact of such changes in form of the bad smells. So this is the implementation I used. I extended a tool called Orc using a model parser and a change manager. So I used another tool called EMF compare here to get the changes between successive versions of models that are stored in GitHub repositories. So I analyzed all the Simulink models in GitHub repositories. I get the changes between successive versions, and then I perform analysis on those changes. So I also use another tool called Massive to help me convert the Simulink models into a tool that can be supported by Orc, into a format that is supported by Orc. So the first part of the work deals with how to recover design decisions. So usually for every repositories in GitHub, for every software you have, there is usually a problem that the software want to address. And usually if the reason why you want to make a change is because maybe there's a problem that occur, maybe you want to add new features, you want to correct a bug or something. So in this case, there's a problem, and these problems are usually documented in issue logs. Now, for every problem, every software design problem we have, there's usually a kind of set of solutions that can fit in to such problems. And these solutions have pros and cons. They have their own implications and gains. So this set of decisions is also possible. It may be discussed in issue log, but finally you have the choice that you made. Finally, maybe due to past experience and the likes, you feel like this should be the best solution to this problem. And this solution that we chosen actually implemented as a set of changes in the commit history of the repository. Often, this set of changes are summarized in commit messages, and the reason why these changes were made are often discussed in issue logs. So traditional approach, just like we've found, actually tend to recover design decisions using both the change that has been made and the discussions in the issue logs to recover the design decisions. But when I went through the issues in the GitHub for Simulink repositories, I found that most of the Simulink repositories, actually more than 60% of them, do not have any issue logs at all. So that means the traditional approach is not feasible and cannot be used in this regard. So I devised a new means to extract the design decisions that necessitate the evolution of software using the type of change and the commit message. So I use a combination of the type of change and the commit message to recover the rationale behind the design decisions. Now, to predict the type of change, I used the four maintenance tasks: the adaptive, preventive, corrective, and perfective maintenance tasks. So I categorized each of a commit message to one of these categories. So to do this, I also employed a machine learning technique using a set of classifiers that has been trained over 300 change sets that I extracted from 28 repositories. So to evaluate my approach, I compared the result I get with the issue logs in two repositories. So I found out that I was able to recover a larger percentage of the design decisions. So out of I cover more than 50 design decisions. Out of those 50 design decisions, about 34 of them actually were actually discussed in the issue logs. So this give me a much more greater percentage of precision. And also, I also discovered that there were some issues that were discussed in the issue logs, about 3 of them, that were missed by my tool. So this is still fairly okay from the discussions we had based on the previous results. Another thing we also did was to match the change type to the labels in the issue logs. So most of the time, every issue has some labels, like maybe this is to fix a bug, maybe this is just for enhancement, maybe this is for correction, maybe this is, and so on. So those kind of labels can also be categorized into change types. So I want to see, does my predicted classifier, the prediction I made based on the changes and the commit messages, does it match the labels in the issue logs? And when after my experiment, I found out that we have a very high F1 measure. So the lowest score we actually had was more than 70. So around 73% F1 measure for the corrective tasks. Actually, but the preventive tasks, we have close to 95% F1 measure score. So this shows like we got a very good result on our classifier. Then the second part is to discuss the immediate impact of a change to the design of a change on Simulink models. And to do this, we want to see what are the impacts of a change on the bad smells in Simulink models. First, what are bad smells? So bad smells are design defects in softwares. They are not bugs because they do not prevent the correct function of the system. So when a software or a program has a bad smell, the program is still able to function correctly, but it may be very difficult to maintain such software. Maybe it's very difficult to adapt such software to changes. For example, when the software has so many duplicates, the software will still function, but if you want to make a change in the first one, that means you have to replicate such changes in like 5 places instead of just one place. So those are like the negative effects of bad smells. So for this work, I identified 4 instances of 4 bad smells in Simulink, and I studied the evolution of these bad smells in 575 models across 31 repositories. And like I mentioned, if I want to I actually target how does changes to the models affect the evolution of smells in Simulink models. So these are the distribution of the smells I got. As you can see from this figure, most of the repositories have like 2 or 3 instances of bad smells, 2 or 3 types of bad smells. And actually 2 repositories contain all the 4 bad instances of all the 4 bad smells. The result shows that most smells are actually introduced in the first version. So the result shows like once you create a model or the first commit you made to the repository actually contain most of the bad smells. And subsequent changes either increases or reduces the instances of such bad smells. And also, addition of new elements often correspond to increase in the instances of new smells. And we also found out that most of the time, adding new features often, that is the adaptive maintenance task, often lead to increase in smells, while the perfective maintenance task that is more focused on things like refactoring or optimal function of the system is actually the one that leads to a decrease in the instances of bad smells in the models. So you can see a graphical figure of the result I mentioned earlier. So we find out that more than 60% of the bad smells are actually contained in the first version of the models. Also, like we mentioned earlier, so most of the adaptive tasks actually lead to increase in this instances of smells, while majority of the perfective maintenance tasks here actually result into a decrease in instances of bad smells. In the future, we would like to focus more on how to recover other aspects of design decisions like the rules and constraints for a given solution. So can we also possibly recover alternate choices like, although this was the choice that was made, what other choices were considered? Can we try to detect that automatically? Also, we want to discuss the bad smells in other system models like Sysmil and see does the result we generate from other system models, are they comparable to the ones in Simulink? And finally, we want to discuss more on refactoring analysis in Simulink model. How do we refactor in Simulink? Thank you.